Okay, so now we would like to test hypothesis that involves statements on population proportion. Now, everything that we've talked about with testing population mean is going to transfer or translate really well with a population with testing population proportion, right? And in fact, it's actually going to be simpler. Okay, so when we test population proportion, we essentially have three different types of statements that we can make. We could say the population proportion equals some number that is a proportion, right? Or the population proportion, or the hypothesis that population proportion is less than or equal to some number. Okay, that will be the setup here, and finally the population proportion is greater than some number, right? Some proportion. Okay. All right. So again, very similar to when we deal with the population mean. Right. This will be a two-tailed test. This will be a right-tailed test, and this will be a left-tailed test. Okay. Now, as with chapter 8, right, when we have population proportion, before we can proceed, we need to determine the normality, meaning we need to know the sampling distribution, and the test is going to be the same. So first, right, establish normality, or determine that the population, or sorry, the sample statistic is indeed normal. Right? We need to use, and we know we've seen this before, n times p greater than or equal to 5, and n times 1 minus p. Oops, sorry about that. We can't write. N times 1 minus p is greater than or equal to 5. So that has to check out. Now, second, we calculate our test statistic. Okay. Okay. Test statistic is going to be in the same form as we have with the population mean. It's just that our formula for the standard error is going to be a little bit different. Again, you've seen this already. So p bar minus p naught, and the standard error formula, I'll just put it on the bottom here, is going to be p naught times 1 minus p naught, the all over n. Now here's the tricky part. With this p, you will be tempted to use p bar for this. Do not use p bar when you calculate test statistic, right? Because we are assuming the null is true when we do our test. Therefore, you must use p naught. Okay. So let me do an example down here, and I think this will become very clear. All right. So here we have a test on population proportion. The hypothesis is that the proportion is 0.2. So the alternative is the proportion does not equal 0.2. So first, well, before we do any of this, to be more formal, we need to determine normality. Right? Is the sample distribution normal? Okay, so here we go. Let's check. Right? Our sample size is 400. Here, write that down here. N equals 400. Right? And my p bar is 0.175. Now, when I test my normality, I need to test it against the null hypothesis. Okay, so my n times 0.20. Should I just write n is 400? Excuse me. 400 times 0.20, and is that greater than or equal to 5? Well, of course it is. There's a really large number that is 80, not 800. I can't do my mental math here. Excuse me. 80. Pardon me. Doesn't matter. That's good. That is greater than 5. So good. That checks out. Whoop. I need to check also. Right. 1 minus p. So 1 minus p is 0.8. Now, that is definitely greater than 5. So check that. Okay. Now we can proceed. All right. Hey, compute the value of the test statistic. Here we go. T equals 0.175. Okay. That's given to us. P bar. Okay. Minus 0.2. Okay, divided by square root of, again here, be careful, we have to use the p that is in null, that is in the null hypothesis. Okay, all right, and the equals, put in the calculator, this is what you should get. Okay, everything else will follow exactly as we did with the population, the population mean. All right, B, the p-value. Here we go. Now here we don't have to worry about whether or not we have sigma, the population standard deviation, because we're dealing with proportion here. So we'll always use the z distribution. Okay, this is a two-tailed test. So my test statistic is there. So really my p-value is actually both sides, both tails. So I want the area of both of these tails. That is my p-value. So here we go. So my p-value. Okay, so what I'm going to do is simply just find the area to one of these tail and then multiply that by 2. Okay, so I'm going to switch. I need to switch over to the normal distribution. Make sure it's 0 and 1. Okay, type in my test statistic, which is 1.25, and get that. So my p-value is going to be 2 times 0.10565. Okay. By the way, if you actually have this app, this app already can do that for you. If you select the option here, you get 2 times that. Okay, 0.21130. But I'm going to do that here on my calculator just to make sure you see that it is the same number. 2 times that. And here we go. Okay, good. 0.2113. So we get the same. So we get the same value there. Okay. All right. C. Let's compare the p-value to our alpha. So our alpha equals 0.05. Okay. So 0.2113. This is clearly much greater than 0.05. Again, that just means our observation is not that extreme. If it's not that extreme, then that means we have no reason to reject our null hypothesis. Right? So our p-value, p-value, it is greater than our alpha, therefore we fail to reject. Right? Okay, or you can say we accept. Right? Accept the fail to reject the null, or we accept the null hypothesis. Right? And either of these statements are fine. Okay. All right. If we are to use the critical value approach, right, then we'll just find the critical. Let's go ahead and find the critical value. Alpha of 0.05. That means my z critical value, right, is 1.96. We found that earlier. That doesn't change. Okay. Again, our test statistic is 1.25. Okay. So 1.25. It is clearly less than that. Right. 1.25 is less than 1.96. Okay, so that means our t is within the acceptance region. Right? Is within the acceptance region. Therefore, we accept the null hypothesis. We fail to reject the null. Either way, whether or not you use the p-value approach or the critical value approach, you will always get the same. You will always get the same result.